This is video 2 in the topic, how does a nuclear power plant work? In this video we're going to be looking at nuclear power.
In this video we're going to be looking at nuclear power. So we're going to see how we get energy out of the nuclear fuel which is given to the nuclear power plants. So in order to understand how nuclear reactions produce energy, it's first really important to have a good image of exactly what a nucleus is. So we know that matter is made up of atoms, and that atoms consist of a nucleus surrounded by an electron cloud. Inside the nucleus we have a combination of protons and neutrons. Now the electrons are really important. They determine all the chemistry and the chemical reactions that an atom is going to undergo. However, for nuclear physics, we completely ignore the electrons and we only consider what is going on inside the nucleus of the atom. So atoms are typically measured in angstroms. They tend to be about 0.3 to 3 angstroms in radius. An angstrom is a unit of measurement which is equal to 10 to the minus 10 meters. The nucleus, on the other hand, is much, much smaller than this. The nucleus of atoms range from 1.75 to 15 femtometers. A femtometer is 10 to the minus 15 meters. Now the femtometer has the symbol Fm, but often nuclear physicists refer to the femtometer as the Fermi. This is in honor of the Italian physicist Enrico Fermi, who won the Nobel Prize in 1938 for his work on induced radioactivity and his discovery of transuranic elements. And both these things are very important for how a nuclear power plant works. So sometimes we will refer to it as femtometers and sometimes as Fermis. They mean the same thing. So to visualize the size of the nucleus in comparison to the size of the atom, imagine that we put a cherry in the middle of a football stadium. The cherry would have the diameter equal to the diameter of the nucleus, and the football stadium is then the distance, the size of the atom. So the radius of the football stadium compared to the cherry is about the same as the radius of the nucleus compared to the atom. Now in volumes, volume of a sphere is equal to 4/3 pi r cubed, so we have an even more extreme effect. Imagine now that you have an Olympic-sized pool. So Olympic pools tend to hold about 2,500,000 litres. So if you put 2.5 times 10 to the minus 3 millilitres of water into that Olympic-sized pool, that would represent the size of the nucleus within the atom. So atoms are mainly empty space. The electrons take up even less space than the nucleus. In fact, electrons actually take up 0 space, which is a very interesting point. But the atom is mainly empty space. So if my hand is made of atoms, and atoms are mainly empty space, why can't I pass my two hands through each other? This is mainly empty space, this is mainly empty space, so what's going on? Well, the answer is actually the electromagnetic repulsions between the electrons in the atoms in my hand prevent us putting one object through another object, which is why we can't walk through walls and etc. So another interesting thing is we've just said that inside the nucleus we have neutrons, which are neutral, and then we're also going to have the positively charged protons. So if we have lots of positively charged protons close to each other, in the first topic you learned about Coulomb's law, which said that like charges repel. So why does the nucleus not just fly apart? Well, it actually comes about because there's actually another force as well that can be found inside the nucleus. So in nature, there are 4 fundamental forces. So far in this course, we've looked at gravity. So gravity is one of these fundamental forces. Any 2 objects that have mass are going to attract each other. And this attraction drops off in relationship to the square of the distance between the 2 objects. you've seen the electromagnetic force. So there's an electric property to this and a magnetic property to this. Coulomb's law forms part of this. But again, the electromagnetic force drops off as the inverse square of the distance. So as we increase the distance between them, the strength of that force drops off as the square of that distance. Now there's also another two forces that we haven't studied yet. There's the strong nuclear force, which happens inside the nucleus, and we've also got the weak nuclear force. We're not going to be looking at the weak nuclear force in this course, but the strong nuclear force is an attractive force which works on the nucleons inside the nucleus. What's different about the strong nuclear force is that it actually has a limited range. Its range is around about 1 femtometer or 1 Fermi. So the strong nuclear force is an attractive force which is related to the number of nucleons. So nucleons is a term which refers to everything which is found inside the nucleus, and what we find inside the nucleus is protons and neutrons. So it means the number of protons and neutrons. So let's now consider how the limited range, so the strong nuclear force, exists between two particles which are within a femtometer of each other. If we go out to larger distances, then there is no strong nuclear force. So let's consider how this limited range of the strong nuclear force limits the size of the nuclei that we can actually build. If nuclei get too big, then there's just not enough force anymore to hold them together. So let's have a look at that in a bit more detail now.
Now imagine that we want to bring two protons together. So here's one proton here, and here's another proton here. Now at this distance they're going to feel quite a strong repulsive force in this direction. Just because of that electrostatic force, Coulomb's law, we know that like charges feel a repulsive force for each other. But what we want to do is we want to do work on them and bring them together within a distance of 1 femtometer. So this is inside a nucleus. A nucleus has a radius of about a Fermi-meter. So we can bring these two in here. Now when they are inside this nucleus, when we've moved them into this distance, they now feel an attractive force due to the strong nuclear force. So when they were this far apart, there was no strong nuclear force because the strong nuclear force has a very limited range. It will only work within about a femtometer. Now the problem is that the nuclear force is proportional to the number of nucleons. So here, while the strong nuclear force is causing an attractive force, the electromagnetic force is still causing a repulsive force, and the electrostatic force is actually larger. So these would actually fall apart. In order to make it stable, what we have to do is add a couple of neutrons in here as well. And then since the strong nuclear force is proportional to the number of nucleons, and neutrons are another type of nucleon, then the attractive force becomes larger, and the attractive force overcomes this repulsive force, and so we now have a stable nucleus.
So as we've seen, the nuclear force is attractive and short range. Now let's consider how we actually work out how many nucleons there are in the nucleus of a given isotope. Now we'll be looking at different isotopes of elements. Different isotopes have the same number of protons, as the number of protons determines what type of element we have, because the number of protons is equal to the number of electrons, and those electrons are responsible for all the chemistry that takes place. So that's what determines the type of element. But different isotopes of the element have different numbers of neutrons inside the nucleus. So in order to represent an isotope, we need to have a symbol. So what we use is this symbol up here. Now the X stands for the symbol which we can look up on the periodic table to represent that element. So for example, with helium, the symbol that we use, we replace the X with an HE, a capital HE, and that stands for helium. The Z here stands for the atomic number. So the atomic number is the number of protons, which determines all the chemistry and what element we actually have. So if you know what Z is, then you can look up in the periodic table and work out what X is. So for helium, Z is equal to 2. It's got 2 protons. Now the symbol here, A, stands for the mass number. Bit confusing because A stands for mass number and Z stands for the atomic number, but the mass number is equal to the number of protons plus the number of neutrons. So the mass number is equal to the number of nucleons. So for helium, we have 4, 2, He, as A is equal to 4, Z is equal to 2, and the symbol is He. Now we can have different isotopes of helium. So for example, 3,2He is a different isotope of helium. It's an isotope still with 2 protons. It has to have the 2 protons to still be helium, but in this case it's got 3 nucleons. So that means that it's got 1 neutron and 2 protons to give it the 3 nucleons. So let's have a look at an example now.
So consider uranium-235. Part A, how many protons does it have? Part B, how many neutrons does it have? Part C, write the symbol for this isotope. So part A, to work out how many protons it has, we actually have to look up uranium on the periodic table. When we look it up, we see that its atomic number is equal to 92. So this tells us that it has 92 protons. Now, 235 refers to the number of nucleons. This is the mass number, which is the number of protons plus neutrons. So to work out how many neutrons, we have to do 235 minus 92. And when we do that, we end up with 143 neutrons. So to write the symbol, we look up the symbol for uranium. It has the letter U. We put the atomic number down here, which is 92, and we put the mass number up here, which is the 235. So that is our symbol for uranium-235.
Now some isotopes are stable and other isotopes are not stable. So if they're not stable, it means that they decay. They break apart and form other types of elements. So let's have a look now at what determines whether an isotope is stable or not, and some techniques that we can use to predict whether an isotope is going to be stable or not.
So what we have over here is a diagram which has the number of protons along the bottom, and up this axis is the number of neutrons. Now you can see for low mass isotopes, such as say helium, in helium, remember we've got 2 neutrons and 2 protons. You can see the stable isotopes for helium lie along this line here, where Z is equal to the N, the number of neutrons is equal to the number of protons. So this is the Z, this is the N. And that's because to have a stable isotope for these low mass ones, the strong nuclear force with the 2 protons and the 2 neutrons is enough to overcome that repulsive electrostatic force. And so to have a stable isotope, we have Z is equal to N for low masses. Now, as we get heavier and heavier, we get larger and larger nuclei with more and more protons in them. So here's a heavy one. Now all of these protons have the repulsive electrostatic force between them. They also have the attractive strong nuclear force. And so we've got lots of neutrons in here. Now the problem is that the range of this strong nuclear force is not quite the same as the size of the nucleus. So the strong nuclear force is limited to 1 Fermi or 1 femtometer, and as we get up into this region of the graph up here, our nuclear radii are getting a bit bigger than that. So our strong nuclear force is limited to part of the nucleus in here. So that means that the strong nuclear force, the attractive force, is only affecting part of the nucleus for this proton, say, whereas that electrostatic repulsion is coming from everywhere. So that means that inside this part of the nucleus, we need more neutrons than protons in order to make that nuclear force stronger than the electrostatic repulsion. So as we get up into this part of the curve, we need more neutrons than protons. And this actually limits the size to which we can have stable nuclei, because at some point this electrostatic repulsion is going to overcome that strong nuclear force. So you can see that on this graph here, the colours refer to the half-life. So a really stable nuclei or isotope is not going to decay, so it's coloured black like this. So you can see the kind of trend that they follow. And then the unstable ones are these blue ones. They have a very short half-life. If you manage to construct an isotope with this nucleus here, it's only going to stay together for a matter of seconds, and then it's going to decay, so it's not very stable. So on Earth, we don't actually get anything heavier than uranium, which is 92, and is this one up here. That's because beyond this, their half-lives are so short that all the isotopes with these atomic numbers have decayed because they are unstable.
Now if we have a stable nucleus, that means that it wants to remain as it is. If we want to pull it apart, we actually need to put in energy to pull it apart. So the amount of energy that we need to put in to completely pull apart a nucleus is known as the binding energy. Now a useful thing to consider is the binding energy per nucleon. So this is how much energy we need to put in for each of the protons or neutrons found within the nucleus to completely cause that nucleus to come apart. So this graph here shows the binding energy per nucleon for all the different elements and isotopes. So the most stable isotope is iron 56. This has the highest binding energy per nucleon, and so per nucleon we have to put in the most energy to pull iron apart. So basically all the elements would really like to be iron. They all want to be as stable as possible. So the lighter elements will tend to undergo fusion, which means they'll tend to stick together to try and turn into bigger elements which are more like iron. The really heavy elements, on the other hand, like uranium, will undergo what's called nuclear fission, where they'll try and fall apart in order to make smaller nucleus, which is more like iron. So this is really important in nuclear power plants. It's how we get energy out of nuclear reactions. So this brings us on to some really exciting physics. We've discussed a bit about Einstein before, but one formula that Einstein is really famous for is E equals mc squared. So we're going to be seeing how to use that now. So when nucleons come together, they actually release energy because they're forming a more stable state. And when they release energy, there's actually a change in mass associated with this as well. So that amount of mass change is given by the formula E is equal to mc squared. So in this formula, E is the energy in joules, m is the mass in kilograms, And c is the speed of light in a vacuum, which is equal to 3.00 times 10 to the 8 meters per second. So let's look at an example now where we can calculate the mass defect and use this to calculate the energy that is released in an example of a nuclear reaction.
So the question is, a 4,2 helium nucleus has 2 protons and 2 neutrons. The 4,2 helium nucleus has a mass of 6.6447 times 10 to the minus 27 kilograms, while a proton has a mass of 1.6726 times 10 to the minus 27 kilograms, and a neutron has a mass of 1.6749 times 10 to the minus 27 kilograms. A. Calculate the mass defect of 4,2 helium. B. Calculate the binding energy of 4,2 helium. C. Calculate the binding energy per nucleon of 4,2 helium. Okay, so to answer part A, we need to use the fact that the mass defect is equal to the mass of the constituents so that's the total mass of the protons and the neutrons that are combined in order to make the nucleus minus the mass of the nucleus. Okay, so the constituents that go in, we have 2 of these protons, so this is 2 times 1.6726 times 10 to the minus 27, and then we've got 2 of these neutrons as well. So this part is the mass of the constituents, and now we have to subtract off the mass of the nucleus. So we're told the mass of the nucleus here, so this is 6.6447 times 10 to the minus 27, and everything there is in kilograms. And so solving this on the calculator, we get 0.0503 times 10 to the minus 27 kilograms is what's lost. So that's the difference between the mass of the protons and the neutrons and the mass of the nucleus. So this is going to be lost in the form of energy. But this here is called the mass defect. Now part B asks us to calculate the binding energy. So now that we've got the mass defect, we can use E is equal to mc squared in order to get the binding energy. So this mass here is the mass defect, so that's 0.0503 times 10 to the minus 27, and then times c squared, so 3.00 times 10 to the 8 squared, and solving that we end up with 4.53 times 10 to the minus 12 joules. Now this is a very small number, and so often in nuclear physics, rather than using joules as the unit for energy, we use electron volts or either mega electron volts. Now in order to convert from joules to electron volts, what we have to do is divide by E, the charge on an electron, which is 1.602 times 10 to the minus 19. So when we divide this energy by 1.602 times 10 to the minus 19, we get 2.83 times 10 to the 7 electron volts. And then if we wanted in mega electron volts, mega means times 10 to the 6, so this is equal to 28.3 mega electron volts. And so often this is a unit that is used to express these binding energies, just because it's more convenient. 28.3 is a nicer number than 4.53 times 10 to the minus 12 joules, or at least it's easier to visualize. And now part C wants our binding energy per nucleon, and so all we need to do is divide our binding energy, which is the 28.3 mega electron volts, by the number of nucleons. So this is equal to 28.3 on 4, because there's 4 nucleons, 2 protons and 2 neutrons, and so we have 7.06 mega electron volts as the binding energy per nucleon.
So iron and a lot of the isotopes we see around us every day are fairly stable. They tend to not decay, They will just sit there and their nucleus is not changing with time. Other isotopes are less stable. They'll undergo what's called spontaneous decay. So for example, uranium-238, which is a uranium nucleus with 92 protons and 238 nucleons, tends to decay into thorium-234 by releasing radiation. So in a little while, we'll be discussing how half-lives relate to how stable a nucleus is. But first of all, let's consider 3 common ways for a nucleus to decay. Nuclei can decay by releasing alpha, beta, or gamma radiation. Now, whenever a nucleus decays, it still obeys the important rules of physics. So in particular, it obeys conservation laws. So there is conservation of mass/energy, that is, it obeys E equals mc squared. If it loses some mass, then it is releasing a certain amount of energy. Linear momentum is conserved, like we saw in car crashes. Angular momentum, which is related to the momentum of going around in circles or rotating, is conserved. Electric charge is conserved, so we're not creating or destroying positive or negative charges. And the other thing that is conserved in nuclear reactions is the number of nucleons. So the total number of neutrons plus protons remains constant. So let's start by considering alpha radiation. In alpha decay, a helium nucleus, which is a 4,2He, is released. So one example of this is the decay of uranium-238. So we can write this decay as U-238-92 decays into thorium-234-90Th plus that alpha particle, which is the helium nucleus, 4,2He. So in alpha decay, we always get this helium nucleus released. And so we can write an equation to describe alpha radiation in general, or alpha decays in general. These are known as transmutations because we start with some parent nucleus and it forms some daughter nucleus plus an alpha particle. And so we can write that the parent nucleus with atomic number Z and mass number A gets converted into a daughter nucleus with atomic number Z minus 2 and mass number A minus 4 plus the 4,2 helium nucleus. So you can see here that the number of nucleons is conserved across this reaction. On the left-hand side, we have the number of nucleons is equal to A. On the right-hand side, we've got A minus 4 plus the 4, which are in the helium nucleus, so A. So number of nucleons is conserved. Now let's have a look at the mass energy conservation to work out how much energy is released in the decay of uranium-238 to thorium-234.
So the problem is an atomic mass unit U is 1.6605 times 10 to the minus 27 kilograms. The mass of 238 uranium is 238.0508 atomic mass units. The mass of 234 thorium is 234.0436 atomic mass units, and the mass of helium-4 is 4.0026 atomic mass units. Calculate the energy released when uranium-238 undergoes alpha decay to become thorium-234. So the first thing we need to do is write down the equations for what's going on. So we've got 238 uranium. Now because it's uranium, it has an atomic number of 92 and it's decaying into 234 thorium. Thorium has an atomic number of 90 plus the helium. Now what we're going to need to do is work out the mass of the left-hand side and the mass of the right-hand side, and the difference is going to be the mass defect and that mass defect is converted into energy. So the change in the mass, well, we know it's going to be a mass loss, so we'll write it as the initial mass minus the final mass, and that'll just get rid of that negative sign for us so that we'll end up with a positive answer. So we've got the mass of the uranium-238, so that's 238.0508 minus the mass on this side, which is the 234.0436, plus the 4.0026, and everything here has atomic mass units. So this is equal to 0.0046 atomic mass units. And so now to calculate the energy, we can use E equals mc squared. So this is equal to 0.0046. And now let's get the mass now into kilograms. So we can times this by 1.6605 times 10 to the minus 27 kilograms. And then times c squared, so 3.00 times 10 to the 8 all squared. And this gives us 6.87 times 10 to the minus 13 joules. Now, as we said before, electron volts are a more useful unit. So the energy in electron volts we divide by 1.602 times 10 to the minus 19. And that gives us 4.29 times 10 to the 6 electron volts, which is equal to 4.29 mega electron volts. And so that's the amount of energy that is released.
So the next type of decay is beta decay. In beta decay, a beta particle, which is commonly known as an electron, is released. So how this actually happens is that a neutron inside the nucleus is converted into a proton and electron. So you can see here that the amount of charge is conserved because a neutron has no charge and it's converted into a proton with positive charge and an electron with the same amount of negative charge. So in this case, the atomic number, Z, actually increases by 1 because we're gaining a proton. The mass number, however, remains the same, as the number of protons plus neutrons remains the same, as that neutron is changed into a proton. So an example of this is the decay of thorium-234 into protactinium. So this can be written as thorium with 234 nucleons and 90 protons gets converted into Pa, which is protactinium, which still has 234 nucleons, but it has an extra proton now, so its atomic number is 91, plus the beta particle, which is the electron, which has the symbol 0, because there's no protons or neutrons there, so the number of nucleons is 0, and the atomic number is actually -1, because it's like removing a proton, and the symbol is E. So the general formula for beta decay is that we have some parent nucleus, so it's got some symbol, say P, with atomic number Z and mass number A, and this decays or transmutates into some daughter nucleus with symbol D, and it's got mass number A and atomic number Z plus 1, plus the beta particle with symbol 0, -1, E. So let's now use E equals mc squared to calculate the amount of energy that is released when thorium-234 undergoes beta decay.
So the question is, one atomic mass unit is 1.6605 times 10 to the minus 27 kilograms. 234 thorium has a mass of 234.0459 atomic mass units, and 234 protactinium has a mass of 234.04330 atomic mass units. Part A, write an equation describing the beta decay of thorium-234. B, explain why the mass of the electron is not included when calculating the energy released. And then C, calculate the energy released in this decay in joules and mega electron volts. Okay, so part A, we know that the beta decay is 234 thorium, and thorium has 90 protons and it decays by the release of an electron, giving us 91, because 1 plus 90 gives us the 91, which is protactinium, and we've got 234 here, and so we have 234 on this side as well. So now we've written down the equation. Now it says, why do we not include the mass of this part when we work out the mass defect, which is what lets us work out this mass in C? Well, 234 thorium has 90 electrons around its nucleus when it is in atomic form, because we know that the number of electrons is equal to the number of protons. And so this is just, if we're considering the neutral atom, then there's 91 electrons. So if we're considering just a neutral atom, then there's the 90 electrons here. Now this protactinium, when its nucleus forms, it will capture an extra electron, as it starts with only 90 electrons, and in order to be electrically neutral, it needs this extra electron here. So this extra electron can be captured by the protactinium and just becomes part of the atom. And so that is already included in our atomic masses here. The other reason that we don't need to include it is that electron masses are of order 10 to the minus 31, while protons and neutrons have masses of the order 10 to the minus 27 kilograms, and so this is tiny compared to those masses, and so we can neglect it. Okay, so part C, we need to calculate the energy released. So in order to do that, we're going to need to calculate the mass change. Now it's going to be a mass loss, so we'll just do the initial minus the final, which is going to get rid of the negative sign for us. So the initial mass is the 234.0459, that's the thorium. The final mass is the protactinium, so that's 234.04330. which gives us, this is equal to 0.00029 atomic mass units. Now to get the energy released in joules, we do the mass in kilograms, which is 0.00029 times 10 times this mass here, which is 1.6605 times 10 to the minus 27 times c squared, which is 3.00 times 10 to the 8 squared. And solving this, we get 4.33 times 10 to the minus 14 joules. And then if we want to convert it into electron volts, we have to divide it by 1e, which is 1.602 times 10 to the minus 19. So this gives us the energy in volts of 2.7 times 10 to the 5 electron volts, which we can write as 0.27 mega electron volts. And so you can see this is a bit smaller than the energy released in an alpha decay.
Now there's actually a second type of beta decay. In the universe, we've got particles and antiparticles. In the universe around us, we've only got particles. If we had antiparticles, the particles and the antiparticles would meet together and all their mass would be converted into energy. And so that doesn't happen, luckily, because that would be a lot of energy, which would be very damaging to us. However, the antiparticle of the electron is the positron. So it is possible to form positrons in a type of beta decay. So in this type of beta decay, we have the parent nucleus with the atomic number Z and the mass number A, and it forms some daughter nucleus. In this case, the atomic number is Z minus 1 and the mass number is A. And instead of getting an electron formed, we get an anti-electron formed, or a positron formed, which has a mass number of 0 and an atomic number of +1. And the symbol is once again E. So this is an additional type of beta decay. That positron, which is released from that nucleus, would then travel a little distance, but as soon as it met another electron, it would combine with that electron, and we'd use E equals mc squared to get the amount of energy that was released, as they were both converted from mass into energy. So the final type of radiation that we're going to consider is gamma radiation. So in gamma radiation, a photon is released. Now, a photon is a particle of light, so it doesn't actually contain matter. So when we have gamma radiation released, we're not undergoing a transmutation. We just have one isotope and it's being transformed into the same isotope but in a lower energy state, as it's released some energy as gamma radiation. So let's do an example of this now. We're going to revise in this example a little bit of the stuff you've learnt before about how energy and frequency are related, which you saw when you were doing the photoelectric effect right at the beginning of session. And we're also going to have to use our relationship V is equal to F lambda. So let's do that example now.
So the question is, a radium-226 nucleus decays, releasing a photon with an energy of 0.186 mega electron volts. Part A. Is the radium-226 nucleus transmutated in this process? B. What is the frequency of the emitted photon? And C. What is the wavelength of the transmitted photon? Okay, so part A. In this case, the nucleus is just releasing a bit of energy. It's not actually being transformed into something else. So no, it remains the same nucleus. Part B, we need to use our formula E is equal to hf, where h is Planck's constant. We've got the energy here. We'll need to convert it into joules to put it in here, and then we can calculate the frequency. So the frequency is equal to E on h, which is equal to 0.186 times 10 to the 6, and then to get it into joules, we do it times 1.602 times 10 to the minus 19, and then h, that's Planck's constant, 6.626 times 10 to the minus 34. And so then solving this on the calculator, we get 4.50 times 10 to the 19 hertz. Now part C, what is the wavelength of the transmitted photon? Well, we can use C is equal to F lambda to get this. So lambda is equal to C on F. So that's 3 times 10 to the 8 over the frequency, which is the 4.50 times 10 to the 19. And so solving this on the calculator, we get 6.67 times 10 to the minus 12 meters. So that's a very short wavelength.
Now in the next video we're going to be looking at some other properties of alpha, beta and gamma radiation, as we'll be considering medical applications of these types of radiation, and so we'll need to understand a bit more of their properties in order to explain that. But let's now talk about half-lives of particles. So we've said that unstable nuclei can decay spontaneously. We can work out how likely a nuclei is to decay. The decay is a random process, but it is related. There is a probability for it which is related to the half-life of that particle. So the half-life is the time it takes for half of a sample of an isotope to decay. So if we had a kilogram of an isotope, the time it took for us to have 500 grams of that isotope would be the half-life. It would actually take then the same amount of time for us to have a quarter of a kilogram, and then after the same amount of time again had passed, we would have an eighth of a kilogram of that isotope left. So we actually have a decay graph which looks like this. And so let's have a look now at a simple calculation that we can do using the half-lives to work out how much of a sample is going to be left after a certain amount of time.
So the question is, radon-222 is a commonly occurring isotope in nature. It is present in some houses and is a health risk. It is found that 3.0 times 10 to the 7 radon atoms are present in a room. If the half-life of radon is 3.83 days, how much radon is present after 31 days? So in order to answer this, we need to consider how many half-lives have passed. So number of half-lives, we've got 31 days, and each 3.83 days is a half-life. So this gives us about 8.1, which is approximately 8 half-lives. Now each half-life, half the particles disappear. So the number remaining is the initial number, 3.0 times 10 to the 7. Now if it was one half-life, if we had 3.83 days passed, then we'd times it by a half. But as we've got 8 half-lives, we need to raise this factor of a half to the power of 8. So solving this on the calculator, we end up with approximately 1.2 times 10 to the 5 radon atoms remaining.
Now, one property that we often consider with radioisotopes is the amount of activity, which is the number of disintegrations per unit time. So we can write this activity as delta N over delta T. Now the amount of activity is related to the number of particles that we have. The more particles, the more that are going to be disintegrating. So we actually have the equation delta N on delta T is equal to minus N times lambda. Now in this equation, N is the number of particles of that isotope. Delta N is the change in the number per unit time. Delta T is that per unit time. And lambda is what is known as the decay constant. So it's different for different isotopes. And the negative sign is there because the more particles we have, the more decays, and these decays reduce the number of particles that are then present. So let's now have a look at how lambda and the half-life are related. In order to do this, you're going to need to know a little bit about logs. So hopefully you remember a little bit about logs from year 10 at school.
So what we're trying to do is find the relationship between lambda and the half-life. Now we know that delta N on the delta T is equal to minus N lambda. Now there's actually another way we can write this equation. To understand how to derive the other way, we need a bit of calculus. So let's skip the calculus and just say that we can write this as the number of particles present is equal to the initial number of particles present times e to the minus lambda t. Now we know after one half-life, the number of particles has halved. So after one half-life, we've got a half times the initial number of particles is there, and then just substituting in here, this is equal to the initial number of particles times e to the minus, and then we said the time that elapsed was one half-life. So now we've got an equation there. What we can do is remove the common factor on each side, and now we've got a half is equal to e to the minus lambda t 1/2. And so now what we're going to want to do is to get rid of this exponent. So that's where logarithms come in. We're going to have to take the logarithm of each side. So we've got the natural log of a half is equal to minus lambda t 1/2. Because taking the natural log of this exponent here gets rid of the exponent. And so we can write this as minus log 2 is equal to minus lambda times the half-life the minuses cancel out, and we end up with the half-life is equal to log 2 on lambda. So we've now come up with a relationship between the half-lives, which are easy to understand, and lambda, this decay constant.
So as we've just seen, we can actually write the number of remaining isotopes as a function of time as an exponential function. So we can draw a graph like this, showing the number of radioisotopes that remain with time. And after each half-life, the number of particles remaining has been reduced by a factor of 2. So in this video, you've been introduced to nuclear physics. You've seen that nucleus consists of protons and neutrons. You've been shown how to write nuclear equations, and you've been introduced to alpha, beta, and gamma radiation. In the next video, we're going to consider some further properties of alpha, beta, and gamma radiation and their applications in medicine. After that, we're going to be considering nuclear power plants. So we'll be looking at the reactions that actually take place in a nuclear power plant, and you should now have an idea that those nuclear reactions are going to produce energy, and, well, as we will see, that energy is then converted inside the nuclear power plant into electrical energy, which is piped out the nuclear power plant in the form of electricity and can be used in our homes or in society in whatever form we so choose.
Thanks to Sebastian Frick for filming this film, and thanks to these people for providing these images, which were actually copyright free but which we made use of.